Hello, everyone. What I'd like to do now is switch gears and discuss the Lebesgue integral. So the approach I'm going to take to the Lebesgue integral is the same as the approach in Royden's real analysis. The only difference is he does it in two different ways, and I'm going to do the way he does it towards the latter half of the book. So it's, I think, in like the last two-thirds of the book. He does integration theory for general measures using this approach. And it's just a better approach, in my opinion, than the way he does integration in the beginning of the book. Um, and the kind of way we're going to approach this is really just a new way of looking at area under the curve, or rather a new way of approximating area under the curve that is kind of flipping Riemann integration on its head by partitioning the y-axis instead of the x-axis. So, okay. So in particular, let's say I have a function f defined on a measurable set E. So let's say both f and E are measurable. And for graphical purposes, let's say f is bounded. So let's say for some positive number d, f of E is a subset of 0 to d. Right. So yeah, we're going to first look at integrating non-negative functions and then extend it to general complex value functions. We do want to look at complex value functions, particularly for applications to engineering, physics, particularly the Fourier transform and Fourier series. They are complex value. So anyway, all right, so what I'm going to do is, like I said, partition the y-axis, kind of like we did like we usually do for Riemann sums, but where we partition the x-axis. So let's say delta y for some natural number from some natural number n, it's d minus 0 over n. I write it that way because usually if this was a c here, it'd be d minus c over n. Right? And let's say yi is going to be, so these are my partition points for I equals 0 to n. So it's 0 plus I delta y. So it's just I d over n. Okay. Okay. So something to note. This is pretty much trivial. So these intervals from I equals 1 to n partition 0 to d. I mean, the first one, when I equals 1, is just 0 to d over n. And then we go from d over n to d over n, all the way to n minus 1 times d over n to just d. Okay? So this is kind of trivial here. So let's say EI, and I'll throw up a picture in a second. So I'm going to set EI to be the inverse image of this interval here, yi minus 1 to yi. So just like we did for the simple approximation theorem, I'm going to set, I think it's var phi, the standard notation in Royden's book. So let's define the simple function var phi of n as the sum here, I equals 1 to n, yi minus 1 of the characteristic function of ei. Okay. All right. So two things to note. So if x is an e, well, so yeah, if x is an e, then f of x, we're assuming f is bounded, so that f of x is between 0 and d. So pick an I between 1 and n, where f of x is in yi minus 1 to yi. We just said that these partition 0 to d, so I can always pick an I where this is true. So that means, by definition, x is in the inverse image of yi minus 1 to yi. All right, so what does that mean? That means, just going back, well, plug in x here. So x is an ei, so this is going to be yi minus 1. All right. Well, f of x is between yi minus 1 and yi. It could be equal, but it's certainly bigger or equal to. Okay. So, in particular, for any x and e, this is less than or equal to f of x. All right. So also, for any x and e whatsoever, you can check very, very easily. And we did this in that video on the simple approximation lemma, approximation theorem. Okay. So yeah, these functions converge to f, and they lie below f. Okay. Okay. Right. So I'm going to make another claim. This is really a graphical claim, and I'll put up a picture up in a second. So I'm going to claim graphically that the area under f of x, and by that I mean on E, or over E, is approximately the following sum. So these specify kind of the heights. And for nice functions, at least, this is kind of the area, the base, the length of kind of the length of the base of my rectangle. So these are heights. Lengths, these are the lengths of my rectangle. Okay, So yeah, let me immediately put up a picture before I do anything to, well, so that this makes any sense whatsoever. All right, so here is the picture I have. Let's say y is a nice parabola minus x minus 1, x minus 5, or minus x minus 1 times x minus 5. Okay, so just calc 1, it has a maximum at x equals 3, and that is 4. You can plug that in. When x equals 3, it's minus, well, it's 2, sorry, minus 2 times minus 2 is 4. All right. So yeah, in particular here, so E is going to be, let's say E is 1, 2, 5. All right, so let's say I want N is 4. So delta Y is just, of course, 5 minus 1 over 4 is 1. I don't think I need to write that. So yi is just, well, I times delta y is I. So for I equals 1 to 4, I'll graphically show you what EI is. EI is just going to be, well, just go back to the definition, the inverse image of these intervals. So, a bunch of windows here. So this is going to be the inverse image of I minus 1 to L. All right. Okay. So this is going to get crowded here. So I probably should use various colors. All right. So let me start off with black here. Okay. So yeah. So E1 is the inverse image of 0 to 1. Just plug in 1. So this is, remember, we're thinking of, these are partitions of the y-axis from 0 to y equals 0 to y equals 4. So we want to look at the inverse image of this interval 0 to 1 here. Okay? So we're asking, when is this blue curve between 0 and 1? Well, here and here. E1, it's not an interval. It's the union of two intervals. That's fine. Graphically, that's fine. Okay. I guess I'll go to purple here. Okay. Well, what about E2? It's the inverse image of 1 to 2. So when is the curve? When is the parabola between 1 and 2? Well, just here and here. Okay. So here and here are the x values where the graph is between 1 and 2. Do the same thing for 2 and 3. So this is E3. And this whole thing here is E4. Between here and here, my graph is between 3 and 4. Let me go do it this way. Camera is blocking my view here. Okay, so this is all E4. Okay. Right, so yeah, so let's just take a look at this sum here in this case, okay? So when I equals 1, remember here, this, um, this just equals I minus 1. So when I equals 1, the heights are 0. So that's why there's no gray here. There's really no volume. There's no area because we have like a rectangle. We have rectangles of height 1, basically. Okay, so in the case I equals 2, we have y2 is 1, so we have heights of 1, and the measure of E2 is just the length here plus the length here. So we have these two rectangles. So yeah, just fill all this in and fill all this in. So what I'm filling in here is just y1 times the measure of E2. Right, so yeah, so here's what I'll fill stuff in and then write stuff out in a second. So what I'm filling in here, and this is very efficient, a lot quicker. Yeah, so what I'm filling in here is going to be the measure of E2 times the measure of E3 times Y2. Yeah, and you get the point. So here, let me just fill this in very crudely here. Okay, so again, what I'm filling in here is the measure of E4 times Y3. All right, so let me do this here. Move this over a bit. So this is a bit of a long-winded introduction to the point of the Lebesgue integral, but I still think it's worth it because doing the Lebesgue integral this way is very efficient. It's really mind-bogglingly efficient, and how it's mind-boggling really how quickly you can get to very deep theorems like Fatou's lemma, monotone convergence theorem. So yeah, time spent on motivating the definition, I think, is worthwhile. Okay, so yeah, I'm not filling anything in, but here's the E1 is black. So here's what I'll do. I'll say area. Oops. So it's approximately so what I'm doing, I'm simply writing out this sum I equals 1 to 4, but with the colors corresponding to the areas here. So I can't really write it in white because, well, then like literally the background is white. But this here, so I'll just be clear. This here, well, I'll erase in a second. But just to remind you, this is 0, so the whole thing equals 0. Even though, definitely, these intervals here have length. It's just add up the length of these two intervals here. I should say in general, these intervals here, it might not be the same. There's no reason why. In this case, the parabola symmetric about this vertical line. But in general, in general, these sets could be incredibly horrendous. But anyway. And I should point out, actually, I didn't point this out. I didn't mention this, but I really should. These are measurable because we're assuming f is measurable. So if f is measurable, then the inverse image of an interval is measurable, right? So it makes sense to take the Lebesgue measure of each of these EIs. All right, so now let me go to purple. Okay, so what I'm going to write here is the purple area here. So it's Y1, ME2. What I'm going to write is the orange area, Y2M of E3. That's, yeah, and in green, this is Y3, the measure of E. Yeah, so add these up and you roughly get the area under this curve. Now, if just for graphical sake, we only had n equals 4, but, and this is a wonderful app that was made by, I don't see, I forget the guy's name, but I'll definitely put it up in the comments. I actually asked, does there exist a nice app like this for the Lebesgue integral? And on Mass Stack Exchange, and this guy was really, really wonderful and just made it. Just incredible. Thank you very much. This is really wonderful. So so just ignore this vertical black line here. So what I have here, if you ignore this vertical black line, is basically what I have. I mean, I can even put a vertical black line, I guess, on it. But right. So this whole thing from here to here would be E4. These two are E3. These two are E2. And here and here is E1. Right? So you can see as n gets bigger and bigger and bigger, I get a better and better and better approximation of the area under the curve. And to be sure, this one here and this one here would be E1. It's the inverse image from Y0 to Y1. And for example, this would be this one here, and this one here would be E2, the inverse image from Y1 to Y2. Here is where the graph is between Y1 and Y2, and also here is where the graph is between Y1 and Y2. Okay. All right, so let me put up a new paint picture. Okay. All right. So, right. And one thing here, it's reasonable to kind of think that this here is the integral, let's say integral of the simple function phi n. Right? Why is that? Well, what I'm going to do here is I'm going to define let's say in general, I'm going to define the integral, the Lebesgue integral. Again, this is a definition. So if I have a simple function var phi, I'm going to define it in the following way. In general, I equals 1 to n. yi ei. Um, yeah, so I'll do it this way. So here, so this is a simple function. So let's say the image, and so I'm only going to do this for a non-negative simple function. All right, so we're going to assume all of these are non-negative. And let's say EI is the inverse image of each yi. All right, and so right. So one thing I want to be clear when so I want to be clear here is that I want these to be distinct. It's very important. I do not want any repeats here. So in this case, if these two are true, it's basically trivial that my simple function, my non-negative simple function, can be written as some yi times a characteristic function of ei. Right? Right? And I'm saying also in the image is exactly these n non-negative numbers. So we clearly have E is going to be this disjoint union. It's disjoint because I'm demanding that these Y's be distinct.
Okay, so why does this definition that I'm circling here make intuitive sense? Well, the sum here, the right-hand side of what I have circled, can be thought of as the area under this curve over the set E, at least when the EIs are graphically nice. So for example, let's say we have a simple function whose graph is in light blue. on 0 to 14. Why not? Okay. So in this example, this here is going to be, of course, 0. This from 0 to 4 and 12 to 14. This is 0. Open 12 to close 14. 0 to 4. All right. Yeah, we have here's E1. Here's E2. And here's E3. So remember, E1 is where function is 0, E2 is where the function is 2, and E3 is where the function is 4. So of course, n is 3 here. Okay, so obviously the sum here is going to be the area of these kind of the rectangles. So particularly, yeah, so draw these dotted lines here. All right. So first of all, yeah, so we have the area. Well, there's no area because y is 0 on E1. Um, so yeah, area. So intuitively, the area under y equals var phi of x. Is going to equal, and I'll explicitly write out what this is. Second. So let me do this area in red. Y2M E2. And then I'll do this in green. So the green here, Y3 ME3. So explicitly, this is obviously 0, not that it matters, but 0 times 4 plus 2 is 6. The measure of E1 is obviously 6. Y2 is 2. And the measure of E2, 8 to 4 is 4. 2 times 4. Y3 is 4, and the measure of 8 to 12 is 4. For a total of 8 plus 16 is 20. Right. Now, of course, we could have the image to be more than 3 elements. That just would be a little more annoying to write. But you can imagine an example like this where the image was maybe 5 elements, 10 elements, whatever. And as long as the E's graphically are nice, then intuitively, the sum, again, is the area under this curve. So now that makes intuitive sense. Now, real quick, there are 2 subtleties in this definition here. One, particularly involving infinities. I'll explain what I mean by that in a second. So let's do a very easy example where here n equals, I guess technically n equals 2. So let's say E is the real line. And my simple function on E is just a characteristic function, excuse me, of 0 to 1. So the graph of this is pretty trivial. So let's say we have 1 here. Let's say we have 1 here roughly. I'll use light blue again. So okay, so to the left and to the right. Make this as big as I get. That's fine. I'm drawing arrows to indicate that to the right of 1, to the left of 0, the graph is 0. Okay. So obviously this is 0 to 1. All right. So technically speaking, and one thing I want to get out of the way real quick, when I write this, I'm going to follow Royden, use his terminology. So when I write my function like this here, this is called the canonical decomposition of my simple function on E. Usually don't even say on E, but yeah. And so to be clear here, again, the image is the y's where these are distinct. Y1 to yn. So in this case, the canonical decomposition of my simple function is just simply 0 times the characteristic, 0 times characteristic function of r take away 0 to 1 plus 1 times the characteristic function of 0 to 1. So according to this definition, so we know what the area should be. It should just be, well, obviously 1. It's the area under this square. But according to the definition, what do we have? We have this is 0 times the measure of r take away 0, 1. Obviously, it's infinite measure. Plus 1 times the measure 0 to 1. Obviously, it's 1 times 1 is 1. So the point here is we're going to have to define, otherwise stuff just doesn't make sense. We're going to have to define 0 times infinity to be 0 in order for this to make sense. Okay? There's no L'Hopital's rule going on. We do not have any kind of L'Hopital's rule. There's no limits. We're just simply defining 0 times infinity to be 0. So this is a definition, and we need this definition for the theory to make sense. It's that simple. Okay. Otherwise, the integral of this function here is not going to be 1. Okay. Okay, and there's another subtlety that occurs when one of these y's, or let's say yi, is infinity and the measure of ei is 0. Okay. In that case, we still, I mean, we kind of need it to be consistent, but we still define we still define this to be 0. And the idea is, very kind of simple. So at least, so let's say EI is this point here. And so let's say, can't really hard to draw this, of course. Um, I guess that's the only way to draw it, really. Just thinking of this as like a vertical line, sort of. So the area here you can kind of think of it's like infinity times 0, but it has 0 width, so it should be 0. And again, for the theory to make sense, we're going to designate so here I'm saying yi is infinity, so we're going to designate this to be 0. Now, if it happens to be that um one of the yi's is infinity and m of ei is infinity, there's no subtlety there. Infinity times infinity is infinity. Or in general, if one of the yi's is not 0 and we have one of them is infinity, or rather, if yi is not infinity, or sorry, yeah, if yi is not infinity and is not 0, or rather, if yi is not 0 and the measure of EI is infinity, then the product there is just simply infinity. So there's no subtlety there. So for example, gonna have like something silly here, like uh, black. So let's say E is again a real line. And let's say my simple function is something silly like 1 over 1,000, something really small, times a characteristic function, uh, or let's say even 0 to infinity. Right? So the graph of this is pretty clear. So this is nice and small, 1 over 1,000. Make this a little bigger. On the other hand, this is 0. Jump here. Yeah, so according to the definition, what I'm saying here, by definition, this is, we have, well, 0 times the measure of uh, minus infinity to 0. So this is 0, but it's irrelevant. The point here is that there's no subtlety here, and this is perfectly fine. Um, this is just going to be infinity. I mean, that makes perfect sense. Well, this here is infinite area. Because I have the dot, dot, dot. This keeps going. So, yeah. So all, basically that takes care of all the subtleties of the measure of EI being 0 or the YIs being 0 and one of these being infinity. So nothing strange, nothing weird. Um, okay. Well, hopefully that helped. So long. Take care. More videos to come.